Good afternoon, everyone. It's a great honor for me to do the presentation. My name is Xia Wenliang from Aerospace Information Research Institute, Chinese Academy of Science. The title of the presentation delivered soon is Design and Characterization of Relevant Pressure Microsensor based on Parametric Bump. As we know, relevant microsensors have been widely used in many fields, such as aerospace, industrial control, and etc., due to their small sizes and high performance. In order to further improve the performance of relevant microsensors, many methods have been proposed, such as mode localization, synchronization sensing, and internal resonance, which make use of the coupling between modes to achieve high sensitivity and high accuracy sensing. In 2013, a paper published in Nature Physics demonstrated strong dynamic coupling between two mechanical resonators by periodically modulating or pumping the stress of the resonators. That is parametric bump. This strong coupling caused by parametric bump enables coherent transfer of fallen populations between the resonators, thus revealing the possibility of achieving high-speed operation of high-quality factor mechanical resonators. This is one of the earliest studies of parametric bump applied to mechanical resonators. Recently, parametric bump attracted great interest. In 2021, researchers proposed a new approach for enhancing the sensitivity of a relevant MEMS sensor based on parametric bump. The parametric bump periodically modulates the stiffness of the beam, thus creating a virtual energy coupling between two fundamental modes of the beam. And the operation region can be found like this. Can be found that the sensitivity of the relevant sensor can get over 100% enhancement. In 2022, Miao and Zhou published an article in Nature Communications. They demonstrated nonlinear operation of electromechanical fallen cavity systems. By controlling the parametric bump, nonlinearity mediated digitization and amplification in the frequency domain can be achieved, which can be exploited to build high-performance MEMS sensing devices based on fallen cavity systems. Generally speaking, the parametric bump is applied to compensate the frequency difference between the first and the second mode of the resonant beam. Thus, the two modes can be coupled, and energy can be transferred between them, as shown in the left figure. Another explanation for this coupling is that with the parametric bump, there is a sideband of the second mode near the frequency of the first mode, resulting in mixing of the first mode and sideband, as shown in the right figure. Through this coupling, characteristics can be transferred between the two modes so that the characteristics of the sensor can be modulated. Equations of the coupling vibration can be obtained as follows. In order to study the sensing application of parametric bump, simulation and experiments were carried out based on relevant pressure microsensor as above. The pressure sensor is comprised of a glass cap for vacuum packaging and a silicon on-insulator wafer for pressure sensing. Double-clamped beams are fixed on a pressure-sensitive diaphragm through anchors. The diaphragm is deformed by pressure, thus changing the stresses and frequencies of the beam. We can see the electrode configuration of the beam in the center like this. It is electrostatically actuated by an AC voltage AC, and another AC voltage P. Parametric bump is introduced. First, to analyze the theoretical model of the system, harmonic balance method is employed to develop the numerical solutions to the equations, which are the combination of harmonic terms like this. We mainly consider terms related to the first and second modes, that is to say, S takes 0, 1, and 2. Other harmonic terms are neglected due to small responses, like this. We performed theoretical calculations. The results are shown in the figure. Activity the parametric bump at the frequency difference between modes on the certain pressure of 10 kilopascals. It is saying that the first mode is cooled. And the resonance peak decreases. The mode splitting feature becomes noticeable at stronger pump amplitudes. With extra pressure disturbance, omega 1 and omega 2 are changed, and there is a mismatch between omega p and the actual frequency difference between the two modes, so that the distribution of energy between coupled modes is out of balance and mode localization occurs. On the one hand, for frequency shifts, frequencies of the two new modes are separated from each other with pressure disturbance, which is called the varying phenomenon. As we can see, the sensitivity of mode I2 is transferred from about 164 Hz per kilopascal, approximately the sensitivity of the first mode, to 210 Hz per kilopascal, approximately the sensitivity of the second mode. In other words, mode I1 and I2 inherent characteristics of different fundamental modes outside the transition region. In the sensitivity transition region, the two modes are influenced by each other, and sensitivity are changing. On the other hand, as a function of pressure, the sensitivity to amplitude ratio is qualified as about 20 per kilopascal within the linear range, which are relatively over 1,000 times higher than that of frequency shifts. In order to verify the theory of parametric bumps, the designed microsensors have been fabricated as shown in the figure above. The SOI weaver undergoes a series of lithography and etching to form the diaphragm and the resonant beams. Gas caps is etched and then bonded with the SOI, thus achieving vacuum package of the sensor. The finished sensor chip is 9.9 millimeter wide and 822 micrometer thick, as shown in the left figure. Before experiment, the chip was assembled on a cover base. Then, wire bonding was conducted between wires of the chip and pins of the cover base to realize electrical connections. Finally, a cover loop was soldered to the cover base to complete the package. The experiment platform is shown above, which mainly includes a circuit and a vector network analyzer for detecting the signals, a pressure controller for applying pressures, a temperature chamber for temperature control, and a signal generator providing the parametric bump. The figure on the right shows the characterization result of the pressure microsensor without parametric bump. The pressure sensitivities or the frequency shifts of the resonant beam are about 166 and 204 Hz per kilopascal. Under the pressure of 10 kilopascal, the frequencies of the first and second mode are about 54 and 165 kilohertz. With the pressure of 10 kilopascal and the parametric bump applied, the experimental responses are shown in the figure. It is confirmed that the first and the second mode of the resonant beam are coupled. As the pump amplitude increases, the parametric coupling is enhanced, leading to mode splitting. These two figures demonstrate the varying phenomenon and mode localization in a single resonator. With the increase of pressure, the pressure sensitivity of mode I2 increases from about 173 to 202 Hz per kilopascal. The sensitivities of the amplitude ratio in the linear range are about 6 to 7 per kilopascal, relatively over 1,000 times higher than the sensitivity of frequency shifts. As we can see, the experimental results are almost the same with the simulation results. Furthermore, different from mode localization in weakly coupled resonators, the varying points and coupling strengths presented in this paper can be modulated by changing the frequency and amplitude of parametric bumps, making it possible to adjust the layer working range and sensitivity of amplitude ratio of the pressure microsensor. To sum up, with parametric bump applied and extra pressure disturbance, the phenomenon of mode localization is observed in a single resonator, while the sensitivity of frequency shifts of the sensor can be transferred, and the sensitivity of amplitude ratio is much higher than that of frequency shifts. As the varying points of mode localization and coupling stress are controlled by the frequency and amplitude of parametric bump, it is possible to adjust the layer working range and sensitivity of amplitude ratio of the pressure microsensor. Thank you.